Right now, you could, if you really worked hard, you might imagine a time where you could, for $100 a ton, remove carbon from the atmosphere. But since we produce 10 gigatons of carbon every year, $100 times 10 billion is a lot of money, even for Congress. So that's a problem. But of course, things get better and technology can improve it. I have great faith in technology. I think the problem of climate change isn't a technological one, frankly. It's a political one.
Welcome to the Performance Initiative Podcast.
Our goal is to provide you and ourselves with the tools to be the best versions of ourselves.
We are your hosts, Dr. Grant Cooper
and Dr. Zinovy Meyler. We just wrapped up a conversation with the great theoretical physicist Lawrence Krauss.
We solved many of the world's most pressing questions, like we solved climate change.
Also, if you ever wondered, can theoretical physicists perform card tricks? Yes, they can.
Yes, they can. They're very impressive. We finally got to understand questions like what is quantum entanglement, what are wormholes, and a whole lot more. And we were really honored to get the chance to talk with Professor Krauss. Many of you will already know him. He really needs no introduction, but he is the world-renowned theoretical physicist, commentator, best-selling author, president of the Origins Project Foundation, and the host of the Origins podcast. He's held endowed professorships and distinguished research appointments at institutions like Harvard, we won't hold that against him, Yale, University of Chicago, Boston University, University of Zurich, University of California, Santa Barbara. There's a whole lot more. He is obviously one of the leading voices and educators for physics in the country and the world, and it was a real pleasure to get to talk with him.
Yeah, I think you'll enjoy this one. Lawrence, welcome to the show. Thank you for taking the time to have this conversation. And Grant and I were talking before we started, and honestly, we feel like kids in a candy store. There are so many things that we can ask you.
Yeah, absolutely. So we were thinking that maybe we could start about 13.7 billion years ago, give or take a few years, when all of the matter and all of the energy of the known universe was contained in a volume less than 1 trillionth the size of a pen dot on a page, sort of an unimaginably small spot. At that time, what was in that infinitesimally small spot, and where did all that stuff come from?
Well, the answer to a lot of these questions is I don't know. But actually, so let's go back 13.8 billion years, and we'll hope that this conversation takes less time. But so we don't know what happened at t equals 0. We don't have the laws of physics break down. Just a little bit after that, maybe when the universe was a millionth of a billionth of a billionth of a billionth of a billionth of a second old. But we don't know what happened beforehand. As I've written a whole book about the likelihood that the universe spontaneous zero, that space and time, that our space and time did not exist, and they spontaneously came into being. And that's perfectly plausible given the laws of physics. And as I stated, if you asked what would a universe that was around for 13.8 billion years, i.e. our universe, what would such a universe, if it was created spontaneously from nothing, what it would look like after 13.8 billion years? It would look just like our universe. So that doesn't prove anything, but it makes it quite plausible. One thing I should say to make it even weirder than you've indicated, right? There are 100 billion galaxies, each containing 100 billion stars. And it's hard to imagine all of that compressed in a region smaller than an atom, right? I mean, it's just unfathomable. But I'm going to make it even worse for you, because it turns out all that matter, all that 100 billion galaxies, each containing 100 billion stars, that at that early time, that was an infinitesimal fraction of all the energy there actually was. The total energy contained in that region was something like 19 orders of magnitude. Well, no, actually, 19 orders of magnitude more than that. So that was less than one billionth of a billionth of all the energy available at the time, because most of the energy was in radiation, which has since dissipated, if you want, leaving over the matter that we now see. So there was far more energy in very hot stuff than there is that can be accounted for all the matter we see in the universe today. It's really amazing, because the energy of radiation, to be technical, falls as the fourth power of the size of the universe, whereas the energy density of matter falls as a third power, 1 over volume. The density falls as 1 over volume. The energy density of radiation falls as 1 extra power of the scale size of the universe. And therefore, as the universe expands, the ratio of radiation to matter continues to fall because radiation is falling faster than matter. And matter dominates the universe today, the mass of all the galaxies we now see. But early times, matter was an insignificant part of everything. And the total energy density was mostly in radiation, which is now dissipated.
Is that dissipation of the radiation, is that the cosmic background radiation?
Well, yeah, well, that is what the remnant of that is what we see as the cosmic background.
Right.
Exactly. It turns out there was more radiation than just that back early on, but the only remnant of it we can see now is the radiation that's in photons. But in early times, it was in radiation of lots of other stuff, neutrinos and all sorts of other particles that we can't see in that background.
For some reason, for me, the idea that there's all this energy that then dissipates is easier to wrap my mind around than the idea that all of that matter, somehow, it just sort of, and I know you've
started to realize it wasn't really matter then, because when you crush it up at those temperatures, you don't have atoms, you don't even have protons and neutrons. It's so hot, you have quarks and electrons and neutrinos and photons and whatever other particles around. So there's nothing, there's no resemblance of that material to anything today in the sense that matter itself. You don't have squished stars. You
just have plasma or
a hot, dense soup of elementary particles.
Do you ever think about if that soup, right, came out of nothing, and then there was no time because there was no space time at that moment, in a way that my mind can't quite get there yet. But I get that that's real.
Hard to get there. No, it's hard for anyone's mind to get there.
Yeah. Do you think about where did that soup come from? Like, how did that soup get there?
Well, as I say, in quantum mechanics, it could just spontaneously appear. It's allowed to, right? I mean, spontaneously, space in empty space now, there are particles and antiparticles bubbling in and out of existence every second.
Yeah.
And when I light my lamp, when I light my light, electrons are spontaneously emitted photons are spontaneously emitted from the electrons and atoms as they change their energy levels in atoms. And quantum mechanics says that there are lots of fluctuations happening all the time. And in empty space, most of those fluctuations disappear before you can even detect them. That's why they're called virtual particles. But under the right conditions, if you had a big enough electric field or something else, you could pop real particles out of nothing. It would be energetically possible because the total energy of those particles would essentially be zero. They wouldn't. Obviously, you can't pop 2 real particles out of nothing. If the energy is just their mass, because you had nothing and then you have twice the mass of these particles, that violates energy conservation. But if there are interactions if the interactions are such that the interaction energy, which is negative, is more than the rest mass, then the total energy of what you create is zero, and that thing can continue forever. It turns out the total energy of a closed universe, this is if gravity is a quantum theory, then space and time are the quantum variables of quantum gravity, and they're fluctuating. And it turns out if you have a closed universe of space and time, its total energy is zero. And therefore, it's possible as those fluctuations are happening, for a closed universe to pop into existence and persist instead of disappearing.
Yeah. So it's sort of like maybe those things are happening all the time, but then
almost always they have to disappear because they violate energy conservation. But if you create something that has zero total energy, then a virtual thing can turn into a real thing. And so you can imagine space-time, if you wish. There wasn't space-time, but you have virtual universes bubbling out of nothing. Virtual space-time is bubbling out of nothing, and most of the time they just disappear again.
Right.
But one can persist, and under certain conditions, if it has inflation and other things, it can survive long enough to still be around today. But it is amazing that you don't have to do any supernatural shenanigans. It doesn't violate energy conservation. And that's what's amazing. It doesn't violate energy conservation to create a universe that today has 100 billion galaxies, which seems like a lot of stuff. And it looks like, as my friend Alan Guth would say, it seems like the ultimate free lunch, but it is.
Amazing.
Yeah.
This next question is where I'm really going to hopefully not betray completely how lost I might be in this, but is what we're talking about sort of a possible ramification of cosmic inflation and the potential multiverse, in the sense that maybe like our Big Bang was one along a many chain?
Well, no, but you're close. It turns out inflation happens after the earliest moment of creation. Okay, I mean, we think it could be related, and some people have proposed, and I once did, and I didn't write it up, but Alex Logan wrote it up. It is possible that when a universe nucleates out of nothing, it's an inflating universe. It's already inflating. It's already inflating. But that may or may not be possible. What more likely, or what we normally think of, is that the Big Bang happened, and then the configurations of matter and energy as the universe evolved evolved into a configuration where what's called a metastable state, where energy is stored in empty space, and then in that case the universe will start expanding like crazy, and that's inflation. And the hard part with inflation is to stop it. Now, metastable means eventually it will decay into the ground state, right? Like last night there was an ice storm, and as the temperature cooled below zero, you had rain falling and a little puddle, and it was cooling below zero, and the rain was still hitting the puddles, so they were liquid. But eventually they suddenly froze, because the liquid below 0 Celsius, liquid isn't the stable state of water. You want to create ice. And when you do that, actually, by the way, you release energy. So if the configurations of matter and energy in the universe get stuck in some state that stores energy, the universe will inflate. But eventually that energy will be released, and that's actually what would cause the hot Big Bang. Okay, the hot Big Bang that we see, the original hot Big Bang would have been, erased by inflation. Anything that happened before inflation would have been erased as the universe expanded very fast. But the problem is that these phase transitions, if you want to call them, happen locally. So space everywhere is expanding very, very fast, and locally in one place, boom, you basically get you decouple from inflation. That energy is released, and you get what we now would see as the hot Big Bang. But it's local. Everywhere else, space is inflating, is moving, expanding faster than light, in fact.
Yeah.
And so this metaverse, if you want to call it that, is still inflating, and somewhere else the universe is gonna nucleate, and somewhere else. But always there's space between these things that continues to expand exponentially fast. And so in that picture, inflation is eternal.
Right.
It is always expanding, but you can nucleate universes, and these many different universes that you nucleate are part of what we call a multiverse.
Yeah. But then that's kind of what I kind of picture as a tree sprouting branches.
It's right. Yeah, it is a tree sprouting branches. That's one way, depending on how you draw it. That I know Andrea Linde would draw things that way. Yeah.
And so in that sense, like our Big Bang might be one of those branches. Is that?
Yeah, our Big Bang would be one of, an immeasurably large number of universes that might be out there. And the interesting thing about that picture is that in each universe that nucleates, when you leave inflation, it could be that in that universe the observable laws of physics are different in each universe.
Right.
The ground state it falls into might be slightly different in each universe, and in each universe those different ground states would be associated with essentially different laws of physics.
Right.
I've heard you talking about the possibility that the laws of physics in our universe are just an accident.
Right. That's the big question, right? Is this an inevitable outcome of?
Yeah. Are we inevitable? Is there only one law of physics, or one set of laws of physics?
Right.
Or are we an accident? And when I was growing up, I became a physicist because I and all physicists wanted to show why the universe had to be the way it is. And now we find that we may just be saying, well, it is the way it is because it is.
Right. It's turtles all the way down.
Yeah. Well, basically.
Yeah. But what is clear is that if there's a multiverse somewhere, you're asking us about quantum theory and we're explaining.
Well, if there's especially if it's eternal.
Right.
It's only really if it's eternal, right? But as Woody Allen says, eternity is a long time, especially near the end. So infinity is very different than a very big number.
Right.
Because it's so improbable that we'll be in a universe that looks exactly the same, that has a planet like Earth evolving and life forming and history much like our own, and except for the fact that I'm there and you're here.
Right.
It's so implausible that it won't happen if the number is very large. But if the number is infinite, then all possibilities do happen. And
that's another one that's hard to wrap your brain around.
You know, it is. I mean, everything happens. Not only the exact same thing happens an infinite number of times, but also the same thing happens where I change one word. And
right.
Times, and on and on and on. Infinity is a very weird thing.
Yeah. I really like what you said. I think I forget who I think you're a Harvard professor. Who was it? Sidney Coleman.
Oh, yeah.
Said something about it. The problem of trying to understand quantum world is that we're looking at it through a Newtonian space, basically.
Yeah, and then so all this interpretation of quantum mechanics stuff, he would argue is the wrong way around. It should be the interpretation of classical mechanics. The real universe is quantum mechanical.
Right.
So why do you want to interpret it in terms of this kludge, this classical kludge that, it's like trying to describe. We know the universe is curved, right? But if you try and explain what's happening as if the universe is flat, you're going to come up with weird things.
Yeah.
Of course, those weird things are real. They're just an after effect of having using the wrong picture to describe the real thing. And the same thing with describing a quantum world classically. It looks weird, but a lot of that weirdness is just an artifact of having used a classical picture to describe it.
Yeah. We're having enough trouble trying to convince half the country that the globe is round, let alone that
or half
the universe is curved,
or half the country that the 2020 election was real.
Yeah, so the curved universe is going to be it's going to be a hard.
I think science is so much easier than the rest of the stuff. Yeah.
Friends, we hope you're finding value in the content. If you're enjoying what you're watching, please consider hitting the like button, help us with our YouTube algorithm, consider subscribing to the channel, and turn on the notification button to stay up to date with everything going on in the channel. Can we ask you about wormholes? That's something that I've always been curious about. Are those real? Can you describe that to someone who doesn't know anything?
Are they real? The answer is, guess what the answer is?
Maybe.
I don't know.
Yeah, maybe.
The answer to many questions. As I pointed out in my new book, The Geoengineering, that those are the three most important words in science. I don't know. But wormholes are mathematical constructions in general relativity that are certainly mathematically possible. They are shortcuts through space, a curved space. I can't draw a curved four-dimensional space, but a curved sheet can, if I curve a sheet, then I can imagine instead of going all the way up from one place to another along the sheet, I might make a little tunnel between those two parts of the sheet that are bent over. If I take my receipt going around there, I can make a little tunnel. And that's basically what a wormhole is, a tunnel through space and time that connects 2 points, which would otherwise be very distant. But through the wormhole, it may just be a little bit. And if you saw Jodie Foster in Contact, you watched.
Yes. Yes.
And so they're very fascinating because I wasn't the first, but as I described in the Physics of Star Trek, and I think maybe Kip Thorne was the first to write it down. If you had a wormhole, then it could be a time machine. Then wormholes would allow backward time travel.
Yeah.
And that's fascinating because we don't know if backward time travel is possible. It certainly seems to cause problems if you watch any movies.
Yeah.
But you can show that a wormhole will be a time machine. So now we know that wormholes can't exist if the only stuff in the universe is the stuff we see here on Earth or anywhere in the universe. Normal matter and radiation cannot. General relativity. Let me step back. General relativity says the properties of space are determined by the matter and energy and radiation energy within the space. Energy determines the property of space, which then determines how the energy evolves. That's why it's so complicated. But So I can write down a form of energy and momentum that would produce a wormhole. The question is, can I produce that in the laboratory or anywhere else? And the answer is we don't know. But we do know that if that form of energy and momentum is made of anything that we know of existing, that we can create, then wormholes can't exist, because it turns out the mouth of each end of the wormhole will collapse to form a black hole in a time scale shorter than it would take to travel through the wormhole. So, so that we know, and so they're unstable. The only way to stabilize a wormhole is to have some weird energy that happens to have what's called negative energy, some weird stuff that has negative energy that would hold the wormhole open, and you know, we don't know if you can create such stuff. It's an open question.
If you had a crystal ball and you could look into the future 500 years, do you think that we figured that out and that it's possible, or you think?
I don't make predictions that are less than 2 trillion years in the future. for 2 reasons. 1, they're simple, and 2, no one will be around to check to see if I'm right.
Well, 500 years are pretty safe also.
Well, I know it, but 500 years and 100 years and 50 years are all
right.
And I don't know. The answer is maybe it'll happen tomorrow.
Yeah.
So it's hard to know these things. You're always looking, especially when it's theory and ideas and not experiments.
Right.
If you're doing experiments and you have a the breakthrough might happen when you build the damn thing.
Yeah.
But if you're doing theories, you never know what you're going to come up with.
You know, speaking of experiments, there was some hope that when they put together the Large Hadron Collider in Geneva, that they might be able to recreate dark matter, right? Or because they were recreating the conditions of the early universe. Did that ever happen? I mean, the Higgs particle is obviously the most newsworthy that most of us have heard about.
Yeah, that's all it's really discovered so far. Well, it's not quite, but the only major thing it's discovered is that we had hoped it would create things that we now think are the dark matter in the universe, but it hasn't observed them yet, a source of great consternation to many physicists. And the other end is still looking, and there are lots of possibilities. So, you know, it doesn't see something until it sees something. And so the fact that it hasn't seen anything does not necessarily mean that it won't discover something.
Right. Okay, interesting. So we still have some hope. Some hope.
Yeah, some hope, and it depends on your attitude. Yeah, either hope or pessimism, depending upon.
Right.
But I always take the position of my late friend Cormac McCarthy, who told me that he was a pessimist, but that was no reason to be gloomy.
That sounds like Woody Allen could have said that.
Yeah, I know, but it was Cormac, and he didn't. He didn't say much, but he did say that, and I always remember.
Could we ask you about the double slit experiment? That's one that I'm sure you get asked about that a lot. I feel like we sort of have a handle. Let me see if I can tell you at least part of it.
Why don't you tell me about it, and we'll see if you're right.
Okay, all right. So as I understand it, you shoot an electron or a photon towards 2 slits, and it can either go through as a particle or as a wave, and you tend to see it as a wave unless you're measuring it. And then when you measure it, it comes out as a particle.
Yeah. Sorry, the observable is you don't see the wave. What happens is when you put 2 waves through when you put a wave through 2 slits, you get an interference pattern. Out of each slit come 2 separate waves, and those patterns, if you remember from high school physics, produce this beautiful interference pattern. And so if you shoot even a single electron at those 2 slits and you're not observing, then what you'll see is an interference pattern on the screen. But if
that looks like a wave.
Electron detector, then you'll see, then it'll change. Then the electron will have gone through one or the other, and you'll see a lot of brightness behind each slit, but nothing anywhere else.
Right. And that's, so I guess the question and I understand that there is sort of an innate, you know, if you can't get it intuitively, then you probably get it better than if you think you get it intuitively, kind of a thing. But is there something about the measuring that is interfering with the photon as it goes through the slits? That just seemed like the most logical explanation.
It is the process of measurement. Yeah, I mean, when you're measuring a quantum system, you affect it.
Right.
That's
so it's not just that you're watching it.
You don't always change it, but when you measure a quantum system, you the wave function of the system it describes all the possible configurations it can be in, and when you measure it, you find which configuration it is in, at least after the measurement, and that configuration after the measurement need not be the same configuration it was before the measurement. Before the measurement, it was in all different configurations at the same time.
Yeah.
And
then you measure it, and it's just, yeah. Okay.
Yeah, that's pretty amazing. That's Schrodinger's
that is remarkable. I mean, it is truly the most remarkable thing about quantum mechanics, perhaps. Mm-hmm.
Wow. Okay. Because I just thought it made sense to me all of a sudden, like, well, yeah, because whatever you're shining at it or you're receiving it, you're interfering with it, and so you're knocking it out of its normal.
Well, it's not that you're not going to. Well, I mean, that's one possibility. You can knock something out of its normal state when you're observing it, and that relates to the Heisenberg uncertainty principle.
Right.
But the fact that when you measure a system, even if you measure it very carefully, then you are most measurements there. Things can be subtle, but then you generally are taking a system which could be in a superposition of different states. Doesn't have to be. In a quantum mechanical superposition of many different states, and you're basically forcing it to be in one of them after you make the measurement.
Yeah,
that's what looks classical.
Yeah, that's a way that it's easier. It's a little easier to kind of wrap your mind around if you think of it that way.
So. That's why I think.
Right. Could you describe quantum entanglement for us? That's another one that I feel like maybe we understand, but.
Well, maybe we'll see. We'll see if we do.
It's a subtle and often confusing topic, so it's not too surprising. Well, like all of quantum mechanics, it's all impossible to intuitively understand because we are classical beings, but we can try and picture it. So quantum entanglement is really only weird because you think of two objects, two particles originally together, and you think of them as two separate objects. But if they were entangled to begin with, and nothing has interfered with them as they evolve, then they're really part of a single quantum mechanical whole. So it's not too surprising. It's not too surprising you pull a tail on a cat that its face, is not happy. And I mean, that's not a great analogy, but it's an analogy. And so, what's happened is that that you have a quantum mechanical configuration, which is once again these states, these particles are created entangled, but that doesn't mean we know exactly what configuration they're in. Say, take an electron and two electrons in a angular momentum zero state where one spin is pointing up and one spin is pointing down. Well, they can move apart. But there are lots of directions they can be pointing in which they're pointing in the opposite direction. And it turns out the electrons are doing all of that at the same time because they're in the superposition of those states. And then as you move apart, well, what happens is I measure one of them, and my measurement tells me which direction it's pointing in. But that implies the other one must be pointing in that other direction. Mm-hmm. Yeah. So I fix this, and instantaneously that other particle, if measured at the same time, will be pointing in the other direction. Not in every direction, but you could say exactly what direction that would be pointing in if you could communicate. But of course you can't, because light travels at the speed of light. So it is true that if I pick up a phone and I say that electron number 11 that you measured, it was pointing 40 degrees down or whatever it's at. You say, yeah, that's right. But that communication only happens at the speed of light. Right. Before that, there's no measurement you can make here that'll tell you anything about the measurement that was made here. Because you'll make the measurement, the electron will be pointing that direction, but it could have pointed in any direction. So it doesn't tell you that it was forced to be in that direction because you measured this one. If I hadn't measured this one, I could have measured this one first, and I might have measured it being in that direction. 50. Yeah. Another way to think about it is 50% of the time it'll be pointing up, 50% of the time it'll be pointing down. Both those things are true regardless of what measurements I make here. If I record my measurements that call spin up 1 and spin down 0, I'll get a series of 1s and 0s, random series, at this end, and it'll get a random series at that end. And it'll turn out they'll be correlated, but they'll both, for each observer, they'll be random, and no way you could ever tell that there was anything that happened at the other experiment.
If you manipulate one though, if you move one, does that move the other one at the same time?
What do you mean manipulate one? What do you mean move it?
I'm not sure. Like, if you in my imagination, it means like if I could.
No, if you disturb it, then you basically destroy the quantum. I mean, if you disturb it in a way, it's possible to destroy that quantum correlation. If each of those particles interacts with another particle on the way, it could destroy that correlation too. So you have to very carefully prepare it so that those quantum correlations remain, which is part of the problem of maintaining entanglement in quantum computers and elsewhere.
Can we consciously can we entangle particles quantumly? Can we force that entanglement?
Yeah, we do. We do. We can create a quantum state, and then we can put here's the simplest way. It's not simple because you can't do it very easily. But let's say you could smash two photons together. They'd produce an electron-positron pair. Okay, because they annihilate, and that electron-positron pair would be correlated quantum mechanically. Their spin would be dependent upon the collision of the. They'd probably be in an angular momentum one state, whatever that means. So their spin would be pointing in the same direction.
Got it.
So there are other ways you can do it. But you can carefully prepare atomic systems and photons to be correlated. If two photons are emitted by a single, in a single quantum mechanical process, they're correlated.
Got it.
And so that's the way people create entangled pairs. So it's not hard to create an entangled pair. It's hard to keep them entangled.
Because once you interact with one, it takes
there's lots of interactions. They go through the atmosphere, they go through the air in the room, and they collide off atoms and bounce off atoms, and they quickly get those correlations quickly evaporate, which is why entanglement is so weird. If it didn't disappear so rapidly, then it wouldn't seem so weird to you.
Right. Okay. Well, this probably bleeds into another question that we were hoping to ask you. So as doctors, we see our field represented in pop culture in horrifically funny and sometimes annoying ways.
Yeah.
And I imagine that with quantum stuff, it's even more so. So we were wondering, like, what are some of the things that you see in pop culture about quantum mechanics or cosmology more generally that irritate you the most?
Well, I try not to be too irritated, but the two, I'll give you one that's extremely irritating and one that's only mildly irritating. The extremely irritating one is when people abuse quantum mechanics to bilk people for money. So there's these people who write the book like The Secret. Say that quantum mechanics means if you want it to happen, it'll happen. You can send your thoughts out into the universe, and you can change the universe by wanting to be rich or wanting to, and that's such bullshit.
Right.
But people buy it up, and some of them go to courses and pay thousands of dollars and all this stuff. So I think quantum mechanics is the most abused part of physics for bilking people out of money. Or people will say if you meditate, you suddenly fly because you're going to go in lower quantum mechanical ground state. So for a while, people used to say that if enough people were meditating, then you'd start to fly, and they claimed they were flying and stuff. But anyway, and people would pay $5,000 to learn how to fly.
I would pay $5,000 to learn how to fly.
And exactly. And if you want to pay me $5,000, I'll but
well, we've heard, I think, like quantum entanglement being used as an example of telepathy, and that's an example. I mean, quantum mechanics is so weird that people use it for absolutely everything. So that's the annoying thing, especially when they take advantage of other people. People lie and abuse it almost on a daily basis. But if it doesn't hurt people, then it's just and it's just that. The less irritating one is just the examples of a misunderstanding quantum. I think I used to love Ant-Man the movie, but the last one, which was a quantum something or other, had nothing to do with the quantum. Everything in it isn't true, and there's nothing about it that could be true. So I mean, you have to.
I don't mind suspending disbelief in science fiction. I do it all the time, but it has to be good enough. If it's beyond a certain level of stupid when it comes to science, then you can't suspend disbelief. And that one was beyond the level of stupid. There are other ones too, lots of them. I mean, Interstellar wasn't. Anyway, it doesn't matter.
In some ways, I feel like using the word quantum is becoming like using the word green for like food. Yeah. Oh, it's green.
Like using the word what?
Green.
Yeah.
It's just, it's like it feels good. It feels like important.
Well, quantum feels smart, and so
it feels smart.
Use that,
and like anything's possible.
Yes.
Yeah. And no, exactly. And you know what? The other thing I hate is the word quantum leap. Right? Make a quantum leap. That's supposed to be a big leap, right?
Well, I like the show.
Anyway.
Yeah, it was a good show in, what was it, like the 90s?
Yeah, I love the show, but the word.
That is
like, really you made a quantum leap in technology. Oh, it really means you didn't change things very much.
I have a question about sort of the pseudo. So here's something that I've been so curious about. We spoke with Dr. Eben Alexander, who's this neurosurgeon who had this near-death experience, and then he was talking about all of this research that I just, I don't know enough to really challenge him directly on it. It sounds too good to be true. So the research.
It's true. If he had a near-death experience and he claims he saw a dog or anything, it is too good to be true.
Well, let me tell you the research though. So the research, and there was actually a guy, Bob John at Princeton. He was an engineer, and he used to do research on this too. The idea that you can look at a screen and there's supposed to be random stuffs on the screen or random stuff falling down, and you get like 1,000 people and they all try to use their brain waves to move the thing one way or the other. And what they say they find over and over is that there's a very small but reproducible effect, and they attribute that to quantum mechanics. And so by your body language, I'm guessing that you're all in on this.
Well, generally it's abuse. It's either an abuse of statistics or you can trick people. Here, you want me to trick people? Here's an invisible deck of cards. Can you take it from me, please? Take it. You got it?
Got it.
Take it out of the box. Take it out of the box, but be careful. Okay. Pass the box over to, Grant. Okay. Grant, you look at the cards. Okay. Pick a card. Okay. Take it out of the deck. You know what card it is?
I do.
Okay, turn it around so it's facing the opposite direction.
Oh, well, now you'll see it.
And no, it doesn't matter that I can see it. So, put it back in the deck, the opposite direction. Okay, close up the deck.
Yeah.
Pass it to Zinovy.
Yep.
Okay, put it back. Those cards back in the box.
Yep.
Okay, close up the box. Hand it back to me. Okay,
yep.
It's a remarkable magic deck. It's an invisible deck. It suddenly appeared as real. That's part of the amazing thing. It's like, it's okay. But here's even more amazing. This is just amazing. It's the way the universe works. This is quantum mechanics. Okay. So what was your card?
The 3 of clubs.
3 of clubs? Okay. So I should hold this up all the time so you see there's nothing funny happening here. So the 3 of clubs. So there should be one card here that's turned around, facing the other direction. It should be the 3 of clubs. Is that right?
Yes.
Okay.
We can see it.
Can you see the card?
Yeah.
Oh, I see one here. Hold on. Oh, there's one. Do you see that?
Yeah.
Okay. Now I'd like to ask you to take it out, but you probably can't. Should I look and see?
Yeah, let's see.
No, but it's quantum mechanics. Quantum mechanics is so weird. No.
Amazing. So glad that you were able to prove that.
Yes.
All theory.
Wow.
Well, saying that with quantum mechanics, I could make money doing it.
Yeah. Well, it's nice to see that you've mastered. You can actually empower quantum mechanics into the world. That was really cool, actually.
I know it. That's why I did it.
Yeah. Would that have worked in person or only virtual?
And work in person. Yeah. It's much more impressive in person.
Very nice.
Wow.
Anyway.
I'm flying to Nova Scotia.
Okay.
I'll tickle by that one. That was
that's
great.
a good point.
Yeah.
So can we ask you, we heard you like this one science fiction book, and we wanted to ask you, so The Black Cloud.
Yeah,
we both picked it up, and we're
about 3/4 of the way through.
Yes.
Yeah, it's really good.
Yes. It is good because one of the things that's good about it is it really describes, of course it's out of date, but it really describes the kind of interactions that scientists have and the discussions they have and the kind of things that might happen in
Yeah.
response, and also explains some science, which is lovely. It does explain some science that the way
Yes.
they might have found the nature of the cloud. So that's lovely. I mean, yeah, it's a great
Not to take us off the topic of physics, but what I found, I'm not a science fiction fan, but my friend has recommended a couple, like Three Body Problem. I'm not sure if you're familiar with that one.
Yeah, I've heard about it. I haven't read it.
Yeah, but it's amazing how when the science that's explained is really interesting, but somehow the science fiction captures a lot of the human interactions within that seem much more plausible than some of the fictional books or novels that are written that are non-science fiction. And
Well, I mean, a good song. Well, you know what? The problem is, I wrote a book about Star Trek, and since then I've done a lot of talks with people, with science fiction writers and things. And the important thing to realize is that what makes a good science fiction story is not the science, it's the fiction. If it's a good story, the science is added to make some things that otherwise might not be possible. But it's really not. The best science fiction stories are the ones where the stories is good and the science or the abuse of science doesn't get in the way of the story.
Yeah.
Yeah.
Yeah. Yeah. I think that's kind of what's killed Hollywood is they've gotten away from the stories and into the.
For most part, there are every now and then a good stories.
Yeah. 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 Okay. Can we go back to science for a second?
Yeah.
It's okay.
If you were to look into the next, okay, you just said that you don't like to make predictions, but this isn't really a prediction. This is more like, if you were to look into the next, 30 years or so of cosmology, are there some, it's not a prediction, I'm not asking for a prediction, but are there some elements that we're hoping to see, so some discoveries that we can, reasonably anticipate might be coming down the pike?
Well, look, I always tell people if I knew what the next big thing was, I'd be doing it. Right?
Yeah.
I do know that there are the nature of dark matter. We've got a lot of different experiments in not just in the Large Hadron Collider, but direct detection experiments underground for different types of particles, which any day could discover them. And so we've got those new windows. Anytime there's a new window, I expect new interesting discoveries. So dark matter is one example. And of course, gravitational waves are another example. We've got these new gravitational wave detectors. The James Webb Space Telescope is going to tell us about the earliest galaxies. It'll produce surprises. So basically, I'm willing to say that whenever I look at the new windows, and I'll say whenever we have a new window, something surprising might come out of it. But the fundamental puzzles that we have include things that where there's some possibility of answering them. The nature of dark matter is one. The nature of dark energy is not one that I think will be necessarily answered in this century, or necessarily any century. But it's a much deeper problem. But dark matter, since I happen to think it's all the evidence suggested some new type of elementary particle, and we have experiments that can detect a bunch of the possible candidates, the best possible candidates, I wouldn't be surprised if we discovered them in the next decade or two or three. Or another thing is, I think wouldn't be just surprised if we discovered the existence of other geneses of life, either on Mars or in the oceans of Europa underneath the ice sheets and things like that. Or by looking at the atmosphere of planets around other stars, where there are thousands of planets we can see, we might see evidence for biological systems, that oxygen molecules in the atmosphere, which generally wouldn't exist if it weren't for life. But that's not a unique prediction. You can imagine other ways to produce it. But let's say you saw oxygen. 20% of the atmosphere was oxygen. Well, that only happened here on Earth because life produced it. And maybe, otherwise it was carbon dioxide, and maybe some methane, and, so there might be signatures we would see of planets that would say there are living systems on those planets, which would be remarkable.
Yeah. Something that really tickled me that I hadn't, I didn't know was really a real possibility until I was listening to some of your talks.
Oh, that's
was
nice.
The idea that we might really be Martians.
Yeah, exactly. That's why Mars is a iffier thing, because if we see life on Mars, we won't know if it's not our cousins or not, because no planet is an island.
Right.
And because material can be knocked out from the surface of Mars, and we see it later on, some of it as meteorites that have fallen on Earth, and the place we look most likely is in Antarctica, not because it's special in terms of where they fall, but it's easier to see brown things on the surface of the white.
Right.
I've been there, and rocks that are on the surface are generally coming from up there. And if you see a rock that has the same chemical composition as the rocks we know on Mars from earlier missions to Mars, tells us they're from Mars, and what we now know is that extremophiles, or even microbes, can live in rocks or other things, desiccated rocks, for a long time, long enough, even if it takes 10 or 100,000 years for that rock to amble from Mars to the Earth, it could survive. And so Martians may be our cousins, or since the early atmosphere of Mars was hot and wet, it could be that the life originated on Mars and then polluted the Earth, in which case, indeed, when you look in the mirror, you're looking at a Martian.
Yeah. Right. So it may be that we won't, if life on Mars looks like life here, we'll have to look to Jupiter or somewhere else to see if other kinds.
Well, yeah, but you know what? That's true. But also, yeah, if it didn't look like life here,
then
that would be something. But on the other hand, I also think there's good argument to suggest that even if it was an independent genesis, it would look like life here.
Right.
I made bets that if we discover life under the oceans of Enceladus, which have been, separated from us by an ice sheet, and so therefore likely to be an independent genesis if we discover it, underneath 10 kilometers of ice of this ocean. And so if we pierce down and find life.
Where is that? Is that here? Is that on Earth, or that's in Jupiter?
No, it's Enceladus. We know there are oceans under various moons of Jupiter and Saturn.
Yeah.
Surrounded by ice.
Right.
But if we pierce those oceans and find microbes, well, they've never been in contact with the Earth or whatever. And so they're strongly likely if they're independent geneses. But I've argued that if we measured them, I'd still be willing to bet that they look exactly the same.
Yeah. Well, it's kind of win-win.
Namely, what I'm saying is it's quite likely that there's only one route that works, at least for systems with the selection of elements that our star system has, that there's only one route to an effective living organism, and it involves ATP and something like DNA, and maybe even the same 4 base pairs and the same 21 amino acids or whatever it is. It may be just all chemistry has determined a unique route that works.
Yeah.
It may not be.
Right. That's one of the things that I love about your books is you see the interplay between theoretical physicists and experimental, right? And how they, it's a dance, right? And it is what as you like to say, right? It doesn't matter what you'd like to think it's going to be. It is what it is.
It is, yeah. It's whether you like it or not. It is what it is.
Right, it's not.
The evolution happened whether you like it or not. The Big Bang happened whether you like it or not.
Yeah.
And so, yeah, I mean, that's why physics and all of science is an experimental discipline, but physics is an experimental science. Beautiful ideas are fine, but they don't mean anything unless they're validated by experiment.
Right. Yeah. Speaking of interplanetary, do you think that we will eventually be an interplanetary species? Is that something that we should be trying to do?
No, I think it's a waste of time. Well, it depends what you mean by an interplanetary species. Do I think humans should venture out into the cosmos? That's probably a waste of time. Oh. Should we send evidence of our existence and intelligent entities like small microchips or AI systems? That's a good idea. And then some segment of our intelligence could propagate throughout the galaxy at some point. But humans ain't gonna, because where evolution has made us, I was going to say superbly adapted, not so superbly adapted. I get backaches, and so do you probably. But made us pretty well adapted to live on Earth. Evolution didn't make us well adapted at all to live even 200 miles above the Earth's surface, and much less through interplanetary or interstellar space. And it's also, we're heavy. We're 200 or 150 pound bags of water, and mass is the enemy of space travel. So any sensible civilization that wanted to expand, I think, throughout the galaxy, we might have some colony on Mars sometime. I don't see the real value in that, but we might. but if we want to get beyond our solar system, it's just ridiculous to, I think, sending humans there's so many more sensible way. I can make if I was good enough at some point, and that point need not be now, I could design a chip that would, when it landed on a surface, produce a little chemistry set that would isolate elements and create DNA and build a human.
Mm.
That's a nice way to travel.
Right,
Yeah.
that sounds like a last desperate attempt to propagate.
Well, I mean, I think that's much more. I mean, that's the only way that humans, I think,
Yeah.
are going to go from one A to B. But anyway.
Is there you hear some people talk about we shouldn't be sending out those probes into the universe, because if we do find a more advanced civilization, that doesn't always end well for the less advanced. Do you share those kinds of concerns?
Yeah, to some extent. I mean, it is true that anytime first of all, I think it's so remote that we'll ever meet another civilization that I think it's an academic, hypothetical question that isn't probably ever going to be a worry. Because the galaxy is a big place, and so even I wrote about it probably in most detail, a book called Beyond Star Trek, but you could think of almost every way that you could try and detect life, intelligent life elsewhere, and it's extremely hard, even if it's out there. But if it is, the lesson of history is that when two civilizations have interacted, only one comes out, generally. And often if it's technologically advanced, the one that's technologically advanced comes out. And that's quite possible. I tend to think that a civilization that's sufficiently advanced would simply avoid detection, because they have no interest in us. And why would they? So something that's so much more advanced than us, why would they want to be bothered with us?
Yeah, I mean, I think you would, the answer to that, in my mind, would be, sort of the same reason that we go looking at anthills. Because
but if we already know, but look, that's true. But if you knew everything there was to know about anthills, would you get on a plane and go to Africa or whatever and look at big anthills, even if you already seen them, knew them, and explored them before or whatever, and understood absolutely everything about them?
Maybe it's like a kindergarten field trip, and they're all like, "Oh, we got to go look at these things again."
A sufficiently advanced civilization will just sit around thinking.
Yeah,
I don't know. I don't.
Right. I hear you.
My point here is that assumptions about what is likely or natural to happen are very solipsistic or very anthropocentric.
Yeah.
Because a sufficiently advanced civilization is sufficiently different that their needs, goals, and wants are very different than anything we can imagine.
Yeah. Can I pivot to culture? Yeah. So we've heard you talk about education a bunch. And that's something that's near and dear to us too. And I had the experience recently, well, not too recently, maybe it was a year ago, but I had a patient who was a STEM professor at Princeton, and he was retiring early, and I asked him why.
You thought about stems like plants? Is that what you're talking
about? Yeah, no, he's. Yeah.
Presumably he actually taught something real, like a real discipline.
Yeah, he was an engineering professor.
Okay, well that's I'd rather hear that.
Sorry. Yeah. And he was retiring early, and the reason he was retiring early, I asked him why. I was like, why? It's nice, nice job. And he said he was just so tired of having to watch what he says to his students, and it was just too stressful, so he just wanted it out. And I thought, I understood that from the humanities, but the fact that a STEM professor, engineering, would feel that way was really, at that time, shocking to me. Now, at this time, less shocking, but my question was, how infiltrated do you feel like STEM has become with sort of like a woke ideology meaning that people in hard sciences don't feel like they can really express their opinion?
I think it's the latter fact is ubiquitous. Faculty are afraid to express their ideas in general, if they relate at all to anything that relates to societal issues or non-societal issues, gender, etc. But just because faculty are afraid doesn't mean all faculty are woke. What it means is that there are powerful groups within academia that are policing and controlling the dialogue, in such a way as to make everyone else afraid.
Yeah.
But they're also self-selecting. So they're also in general producing, they're reproducing themselves. That's what bureaucracies do. So they're making rules so only people who think like they do can get jobs.
Mm-hmm.
Right.
But the problem is, now a lot of the people who, right now, I think it's fair to say a lot of those people just have jumped through the hoops. They don't believe the bullshit.
Yeah.
They do what they have to do. They fill out the forms. They fill out the loyalty oaths. They do all the rest because they just want to work and they don't want to be bothered. But, but what happens is, as you do this more and more, you get true believers. And what's worrisome is that those true believers, they get hired at junior faculty level, are going to be later be senior faculty. And so you're going to then have a system populated by true believers. And that's a worry. That is a worry.
Yeah.
Right now, I think it's fair to say most faculty just keep their head low and try and avoid detection.
Yeah.
And do what they're doing. Nevertheless, the assumptions, the implicit assumptions of woke social justice, postmodernist social justice, have already been adopted by the leaders of institutions and the leaders of scientific societies. So it's not even questioned anymore when they say, "Oh yeah," the head of the NIH can say, "Oh yeah, medicine is systemically racist and sexist." It's just, okay. Yeah. I mean, that statement is just so ridiculous
Right.
to make without any evidence. In fact, with a lot of counter evidence. And moreover, and the head of the NIH used to be a friend of mine, if you make that, then resign.
Yeah. Right. Like,
Really believe
what
it.
happened to your organization?
You're not just virtue signaling, which is what they're generally doing.
Yeah.
Then just resign, because obviously you're running an organization that's racist. If you really think that, then get the hell out of there.
Yeah. Yeah. They're like crazy. You want to know
Yeah,
crazy?
it's just so hard because it's being policed not by just the organizations but the students, and it makes it very difficult to nearly impossible to have any real instruction, especially in medicine.
Where they were going to have policing groups that would police, that would police all research proposals. And I mean, the proposals that were made by this group of Princeton faculty were just ridiculous but there'd be an organism that would basically police everyone's research proposals and research just to make sure it was sufficiently acceptable for the point of view of diversity, equity, and inclusion. And just, that's just frightening.
Yeah.
Yeah.
Well, so the what I was going to tell you is that there was in medical school, and this isn't pre-med, this is medical school. There was a lecture, and during the lecture, we know that there are racial differences in prevalence of disease and let's say renal function and so on. And when that was brought up, the body of the student body got up and said that that's racism, and they got up and left. And
it's worse than that. I mean, what's worse than that is there are places where faculty will say that truthful thing and they'll be fired.
Right.
Yeah.
Right.
It happened.
That's what's surprising is how the presidents and the deans, they somehow got captured because it seemed
Well, they're afraid too.
Yeah.
They're not in charge anymore. It's these DI bureaucracies that are in charge. And the presidents first start doing it just to virtue signal, because all presidents are is sophisticated salesmen and con artists. I know a lot of university presidents, and generally that's what they are, because they got to raise money constantly. That's what they do. They wake up, they raise money, they go to bed, and every now and then they dress up and give out something. But rest of they have no existence. They used to be intellectual leaders, but now they're generally failed academics too, at least if you look at Harvard. But anyway, what they have to do is they have to make this calculation. Is it better for me to get out in front of if I think that there's a lot of social media mob or whatever, if I say, oh, we don't accept this racist language, and it plays well with the audience and students, they're going to do it. The minute they don't think it plays well, they'll stop doing it, but they'll do whatever will play well. And they don't have to believe. It's not that they've been captured. They realize it's in their best interest.
Yeah.
Virtue signal.
Yeah.
And
They're
many
just
people
following
virtue
the
signal for
incentive.
that reason, and it's despicable.
What do we do about that? Is there any, do you have any antidote?
No, I'm just joking. I said shoot them all.
Shoot them all.
I'm just joking. Let me make that quite clear. Well, look, I think, if there were a magic bullet, I'd again be doing it. We are trying to educate people, speak about it, write about it, which is what I do. But make people aware of what's what's happening and what people are doing. I think that's a real, because eventually people see how ridiculous it is. And that's exactly what happened with the Harvard professors in Congress. Not that I like Congress interfering, and I don't,
Yeah.
but you could see the ridiculousness of the president of Harvard saying, we're not going to attack these people who say kill all the Jews and destroy Israel because it's free speech. But of course, I just came from a meeting where misgendering is violence.
Right. That's yes. Of course.
That's that kind of, when you see that kind of paradox and that kind of hypocrisy, I think most people, not everyone, but most people can see through it. So hopefully those kind of situations become more and more known, and eventually, the other way is eventually it'll just become so prevalent that maybe people will say, I'm not going to put up with it anymore because I can't function. It'll take a long time. Academics are generally the last people to stand in front and speak out. My friend Noam Chomsky once told me that about the Vietnam War when he was leading the protest. The last people to eventually come around and realize the Vietnam War was wrong and should be stopped were the academics.
Really?
Yeah, you won't think so, but
I wouldn't have thought so. No.
Yeah, he claimed it. Anyway.
Yeah.
Academics, just as I say, most of them just want to be left. They want to be left alone,
Right.
and they want to do their work, and they don't want to be bothered, and they don't, and they're not, and they're particularly timid people, right? Because there's no safer environment than academia, or used to be anyway.
Yeah.
Same with students. All this nonsense about safe places. There's no more safe place than a university, for young people. But to claim that they're not in a safe space because someone might say the word is just ridiculous. First of all, because they should be going to university to be able to confront their ideas, but saying it's not safe is just ludicrous. You can't think of a place where kids are babied more than universities. And not kids, but young adults.
Well, and I think it was, I think you were saying, or you were talking to someone who was saying that if you are in a college environment and you feel safe all the time, then you're really not getting a good education.
You're not learning a damn thing. Exactly.
Right.
If you're not confronting if you're not going outside your comfort zone, then what's the point of being there? Other than to have 4 years of a country club experience and make friends and then, have credentials to get a job or make daddy happy or something.
Yeah. Yeah. And it's changed. I was just saying to someone a little while ago, I went to Princeton and graduated in 98, and the people that I know that are graduating now, it's unrecognizable that the two schools are not the same place.
Well, What I mean, one has to be wary of saying that. I mean, ever since I've been a professor, I've always had older professors say, "Oh, the students today aren't like the students they used to be." And it depends how much of that is true, but you're right. I mean, and in fact, I've heard, at least in one report, and I haven't substantiated it, but I've heard one report that lots of Ivy League students are getting fired from their jobs because within weeks or months after starting them, because they're so whiny and entitled and afraid of doing anything, and responding as victims to almost anything that they're not capable to work.
Wow, that's interesting. Yeah,
and I don't know if it's true, but I bet there's some.
I bet there's yeah. Well, that's I mean, it's like when I say that the school is unrecognizable, I mean the idea that there are ideas that are verboten, that there are things you can't hear, that it's a violation to have to listen to it. Those are the kinds of things that just didn't, they weren't present in the 90s. And now they seem pervasive. Although
no, they certainly do, and it's terrifying at one level. It's terrifying.
Yeah, I will balance this just by saying that my dad is a professor at Princeton, and he says, and he's been there since the 60s, and he says, no, this is just part of the, like things fluctuate. There's
come and go.
It comes and goes, and this is just more of that.
Professor of, though.
What's that?
What's he a professor of?
Psychology.
Of course, he's a doctor too, right?
No, well, he's a professor of psychology. So,
psychology. I think he said oncology. Okay.
No. Princeton doesn't have a med school. No, he's a psych professor.
Okay, well, psychology still is confused as it was in the 60s. So,
well, then I always said to him, I would have thought that his field would have more problems with these kinds of issues than like an engineering professor there.
Well, and some places it is. I know of a psychology professor at a University of Berea College in wherever it is, Kansas, that he was I think he was the head of the American Psychological or Psychiatric, I think the Psychological Association. And he created a survey, a questionnaire with his students on hostile work environments. some of which were extrapolated from real examples at the university. He got fired for doing it because it created a hostile work environment.
Oh, wow.
No.
Yeah.
The irony.
My mom had, she was a kindergarten teacher, and she had Freeman Dyson's grandkids. He had twin grandchildren, and
He had a lot
he used to come into the class and he would do little like cosmology.
Oh, he would come in.
He would come in, yeah, he would come in and do like a little cosmology thing.
Right.
And, you know, as both of us obviously went through pre-med, we went to med school, and I asked Zinovy, had you ever heard of quarks or neutrinos? No, we never got exposed to these ideas, even though, you know, we sailed through our science classes in college. And it made me, and especially with something like quantum physics, it seems like the kind of thing that you would want to start much earlier because it would make it much more intuitive to people.
The problem is well, yeah, but it's hard. I mean, first of all, scientific ideas take 40 years to get into textbooks. I mean, one of the reasons I'm not a doctor, in spite of the fact my mother wanted me to be a doctor, is I dropped biology in high school. And because all it was memorization, which would seem to me like memorizing the parts of the frog and stuff.
Right.
And that was in the late 60s, almost as late as 70, but late 60s, yeah, sometime around 69, 70. Now, DNA was discovered far earlier, but we didn't do the neat stuff about I didn't know about the Krebs cycle. I didn't know about any of the things that now I know about that make biology fascinating. But it was known, but of course it didn't get down to the high school level.
So you think this stuff will come eventually? It's just,
well, there's two things. So it takes a while to permeate down. And also, unfortunately, in the US anyway, most middle school and high school teachers really don't have much of a background in science. Middle school teachers especially, some high school teachers do. But again, their background in science may be 1 year of physics or something. And so they don't feel comfortable talking about things at the cutting edge often. Some, of course, they're great science teachers, and some of them do.
Right.
But so I think that's part of it. And also the problem is that most people, you didn't, but most people who now go through high school don't have to take physics, right? You have to take 1 year, 2 year science, and now we teach biology first, and then chemistry, and then physics,
Right.
the wrong order.
Mhm.
Yeah.
But the reason they do it the wrong order is biology seems touchy-feely friendly.
Mm.
You can see frogs and you can see plants and stuff, and
Right.
and it's a lot of description and it's not a lot of math, and people think, okay, but the right way to teach it should be physics first because it's the basis of chemistry.
Right. Physics to chemistry to biology.
Yeah, but that's not the way it's taught. So by the time people have done their year of biology and maybe a year of chemistry, especially after having experienced chemistry teachers, most of whom are awful. Then who wants to get to physics after that point?
Yeah.
Right.
You may have had to take it in pre-med, but pre-med students. Anyway,
No, science teachers always hate it when the
pre-med
pre-meds
class
come.
once, and I'd never do it again. But
Sorry?
I taught a pre-med class once.
Yeah.
The instructor left, so in the middle of term, I think I had to take over. But it's awful because there's so much pressure to get good grades that
Right.
you don't think about what you're learning. You don't spend time trying to go beyond
Right.
in any way beyond what you have to know.
Yes. So the science teachers always hated the pre-med students in the class because.
Well, no, or their whole pre-med classes. It's not that they hate them. It's just they hate their behavior because unfortunately the kids can't allow themselves to be interested. And again, there's exceptions. And I know kids who I taught who were big exceptions.
Yeah.
But there's a great apocryphal story about a physics teacher teaching medical students. But I don't know if I have time for it. So anyway.
What do you want to know?
Well, if you want, I'd
Yeah,
certainly-
please.
Okay. So there's a thing called Atwood's machine, which is you learn about in first year physics, which is some device with a bunch of pulleys and other loops and weights and all this stuff, and you're using an example of pulleys and forces and stuff, and some kid put up there and said, "What's use is the Atwood machine? What's it used for?" And the professor said, "What do you mean what use? It saved countless thousands of lives." And the person said, "Well, how?" And he said, "By keeping idiots like you out of medical school."
That's great.
Yes.
But I didn't know the person said it. But anyway, nowadays you couldn't, of course. Now you'd be fired for that.
Right.
Right. That's violence now.
Threats, hostile, unsafe environment, all sorts of stuff.
That's hilarious.
Yes,
All right,
anyway, go on.
let me ask you one final question before we gotta let you go. But climate change. It's a real quick
Yeah, like a 2-minute topic.
2-minute topic. We know about your the physics of climate change was a great kind of non-political book of yours about.
I tried to make it that way. Yeah.
Yes. For just like a summary of how serious should we take climate change, and what should we be thinking that we should all be doing about it on an individual or country level?
Well, it's how seriously.
In 30 seconds or less.
The Earth is flat and the climate is changing. So how seriously do you take the Earth isn't flat? The Earth is round and the climate is changing. So how seriously do you take the fact that the Earth is a sphere? Well, you take it seriously. Do you think about it every second of the day when you wake up? Probably not. But so climate change is happening, and it's going to have implications. It's already had implications, and it's going to have. And that's undeniable. That's sound science, and it's already happening. You can measure sea level rise. You can measure lots of things. Then you can say, well, is it going to destroy the world? Well, probably not. Is it going to cause things to get really bad in some places? Yes. It's going to get better in some places, maybe. And is it better to do nothing about it or wait till those problems arise? Or is it better to think about, well, we even don't know all the detailed problems. The most significant problems are a little more uncertain than maybe the less significant problems, except for sea level rise. And so is it better to wait and do nothing, or is it better to say, well, what I like, I don't think I put it in the book, but one of my favorite movies used to be the Clint Eastwood Dirty Harry movies.
Sure.
And you may remember he'd sort of be pointing his gun at this awful criminal, and he just accorded them, and the guys look up and say, I can't remember whether I shot 5 shots or 6 shots. This could be empty. Are you feeling lucky, punk?
Yeah.
And that's the question. Are we feeling lucky, punks? Is it better to try and do things that aren't going to hurt society or make things worse? Say, well, I'm feeling lucky. I mean, I think and it's up to people to decide that.
Yeah.
I think there are big lies. The big lies are that climate change isn't happening, or that, well, that's a big thing, or that the change that's happening is not at all induced by humans, and that all predictions are unreliable. Those things are not true. But worse than that, are the arguments that, I think that all actions to address climate change hurt the economy and hurt people. I think that's wrong. There's a lot you can do that doesn't. In fact, there's a lot you can do that makes things better. You can inventing new technologies generally produces economic benefits for everyone.
Yeah.
And or for almost everyone. And so I think the big concern is people who argue that in order to address climate change, we have to take away everyone's cars now, and no one can have lights on after 6 o'clock at night, or blah blah blah. And that doesn't help anything, and it just creates a climate of fear, which always gets in the way. So I think what we can do, like anything, is educate. You asked me what we could do about changing the woke situation in universities, is try and explain to people what's happening. And then I think rational people will eventually vote for rational people, and those rational people might make rational public policies. That's the hope. It doesn't happen very often. It doesn't, but the opposite happens all the time, which is that you can't really have a rational or sensible democracy if you don't have an informed electorate at all.
Yeah.
Seeing the consequences of that, I think, right now.
Yeah.
Individuals, it's such a daunting problem that individuals say, well, there's nothing I can do about it. And there is, it's true, except you can try and educate people around. You can talk to them. And there are simple things you can do. I mean, you can try and think about your carbon footprint or what your children's, and you might think about things you can do or ways you can maybe use sustainable technologies or eat certain things or not eat certain things, and decide if it makes if that's satisfying and or ways to make it feel satisfying. So I
Yeah.
think, I think the mostly what you can do is vote and tell others, or at least speak out in your community and try and encourage information flow, real information flow.
Do you think our way out of it is going to be to develop ways of carbon capture, or do you think that it's basically just adaptive? You know,
I think I think that adaptation is going to be the largest thing. I mean,
Yeah.
it's going to happen, and I don't have great optimism that society is going to make the necessary changes before we have to adapt. And some places will be lucky to adapt. New York City will be lucky to adapt, but Bangladesh may not, right? Which is the
Right.
real problem. Or as you know, if you're reading my book, the South Vietnam, the Mekong Delta
Yeah.
may not. But although I have
that's-
more hope for the Mekong Delta because I'm very impressed with what the Vietnamese and Cambodians could do. But I think so I think carbon capture is so adaptation will be the first thing. Well, we should do that no matter what, because
Yeah.
things are changing. So we should look at ways to adapt and look at ways we can help the third world adapt.
Mhm.
And the first world should be looking at that. Really, it's
Yeah.
not going to happen again, but it should be. Carbon capture is really, really hard to imagine how you can make it efficient, but I think research into carbon capture should continue.
Yeah.
It's just the problem of it is so daunting that it's hard to imagine. Right now, you could, if you really worked hard, you might imagine a time when you could, where you could for $100 a ton remove carbon from the atmosphere. But since we produce 10 gigatons of carbon every year, you know, $100 times 10 billion is a lot of money, even for Congress. And
Give them
and
time.
so that's a problem, but of course things get better and technology can improve. And I have great faith in technology. I think the problem of climate change isn't a technological one, frankly. It's a political one.
Hmm.
But I think I wouldn't be surprised if probably what the world is driven to is geoengineering. Is somehow reducing the solar flux getting through the atmosphere, for better or worse. I think that's probably what we do.
Can you reducing the solar flux getting to
Putting aerosols in the atmosphere that absorb radiation or reflect it,
okay, yeah.
and so you don't have that radiation. So some people talk about blocking out a little bit of the sun too. I mean,
Right.
anything that reduces because it's all physics, right? Energy in equals energy out means that things aren't changing.
Right.
More energy in than energy out means things are heating up, and so you want to change that from more energy in to energy out to make it back to equilibrium again. It's just physics. It's just simple physics. High school physics. Medical students could understand it.
Wow, you're giving a lot of credit over there.
I'm reaching, but maybe that's a good way to end.
Yeah,
Yes.
no, Lawrence, thank you. You've been
Thank you
so
very much.
generous with your time. Thank you so much.
It's been a pleasure. Thank you.
Friends, thank you for your attention. We hope you've enjoyed the conversation. If you find value, please remember to hit the like button, help us with our YouTube algorithm. Consider subscribing to the channel and turn on the notifications so you can stay up to date with everything going on with the channel. And please leave us a comment, let us know what you thought about the show and also what you'd like to hear about in the future.